Okay, everybody, welcome back. This is the second part of Chapter 12. We're going to be talking tonight about sections 12.3, 12.4, and 12.5. This is the second part of Chapter 12 on statistics. In 12.3, we are going to be talking about measures of dispersion, and in 12.4, measures of position. Okay, in section 12.3, we continue with the concepts of statistics, and we go into measures of dispersion. When we're talking about statistical dispersion, we're talking about how the data are spread throughout the distribution. Earlier we spoke about the central tendencies, mean, median, and mode, and while those are important, they really don't help us with all of the information. We need to measure, we need something to measure the dispersion of the data, and two of the most common are the range and the standard deviation. The range is the easiest one to calculate, and basically the range is given by the greatest value in the distribution minus the least value in the distribution. And if you turn to page 659, we'll look at a couple of exercises that illustrate this. Exercises 3 and 4. And in exercise 3, we have some data here: 2, 5, 6, 8, 9, 11, and 15. In calculating the range, we take the smallest number, which in this case is 2, and subtract it from the largest number, which is 15. So the range is 15 minus 2, or 13. In number 4, the data here are not placed in order, but let's say, let's write them out anyway. 6, 5, 10, 8, 9, 15, 22, 16, and 5. So here we're looking at the smallest number, which is 5, and the largest number, which is 22. Now, it doesn't matter that you have more than one 5 here. The range is still calculated as the highest number minus the lowest number, and we get a range of 17. So this is just an indication of the an example of the calculation of the range, which is the easiest of the measures of dispersion to calculate. The standard deviation is a little bit different, and the best way to illustrate this is by using an example. Let's say you and your friends have just measured the heights of your dogs in millimeters, and you've got 5 dogs, or 5 dogs altogether. Then the heights of the shoulders the dogs are as followed here, and they're actually plotted on this chart. As we learned last time, we learned how to calculate the mean. We sum up the individual values, and then we divide by the number of values that there are. This is the arithmetic average, remember, and it is illustrated by X bar, X with a bar over top. The average height, then, the mean height, is 394 millimeters. So on our chart, this is the green line. The standard deviation is a formula based on the deviation from the mean. Remember, the mean is x bar. So the individual deviations from the mean have to be squared, summed up, and then divided by n minus 1. And then the entire value taken, the square root of that is taken. This standard deviation, S, is sometimes referred to as a Greek letter sigma, a lowercase Greek letter sigma, or sometimes as SD. So what we do here is we calculate each dog's difference from the mean. That's the x minus x bar value, x being the individual dog height measurement. We calculate the variance by taking this difference, squaring it, and then averaging the result. So what we have here in this dog height example, in the left-hand column under x, the individual x value, 600, 470, 170, 430, 300, and that averages to 394. That's the x bar. And the n equals 5. That's how many there are. Now, when we subtract the mean, the x bar, from the original x value, there's a column there marked x minus x bar, you'll notice that there's an interesting property here. If you add up x minus x bar, the sum is going to equal 0. This is the case every time. So what we do is we square the difference. So that's where x minus x bar squared comes from. So that 206 squared gives us 42,436, and so on. Then what we do is we sum up the squared differences to calculate the variance. The variance is the sum, the big Greek letter sigma there refers to a sum of the differences, and we divide that by n minus 1, which in this case is 4. That variance is 27,130. The square root of the variance is the standard deviation. In the case of our example, 165. So the variance is either s squared, or sometimes referred to as lowercase sigma squared. Sigma is this little circle with a tail at the top. And the square root of the variance is the standard deviation. So we can plot this on the chart with our dogs, and we can show by the blue line, we can show which heights are within one standard deviation of the mean. Now, this is useful because this allows us a way of having a standard way of knowing what's normal, what's extra large, or extra small. Now, if you had a large population of dogs and you measured their heights, they would have what is called a normal distribution. We'll talk about that here shortly. So to rehash, the standard deviation is one of the most useful measures of dispersion, and it's based on finding the deviations from the mean. That is how far an individual value of x is from the mean. So you calculate x bar, the mean of the numbers, find the deviations from the mean, x minus x bar, square that deviation, sum up those square deviations, divide the sum by n minus 1, and then take the square root of your quotient. In formulaic terms, this is what it looks like. S equals the square root of the sum of x minus x bar squared divided by n minus 1. And the sum of the deviations for a set of data are always going to be 0, which is why you square them. So let's go back to our example. And let's see what they look like here. In example 3, or this is exercise number 3, page 659, we have a value of x, which is given as 2, 5, 6, 8, 9, 11, and 15. So let's calculate the average of these values. So 2 plus 5 plus 6 plus 8 plus 9 plus 11 plus 15 equals, there are 1, 2, 3, 4, 5, 6, 7 numbers divided by 7. This gives us an average. X bar equals 8. N, that is the number of items that there are, is 7. So let's look at the deviations from the mean. This is the deviation score. Which is x minus x bar. So 2 minus 8 is negative 6. 5 minus 8 is minus 3. 6 minus 8 is negative 2. 8 minus 8 is 0. 9 minus 8 is 1. 11 minus 8 is 3. 15 minus 8 is 7. Now, if we were to sum up these deviation scores, we would find that the sum is 0. This is a way that we can check that we did our deviation scores correctly. Now we're going to square these deviations. So negative 6 squared, this gets rid of the negative number, 36. Negative 3 squared is 9. Negative 2 squared is 4. 0 squared is 0. 1 squared is 1. 3 squared is 9. And 7 squared is 49. Now we're going to create a sum of the squared deviation scores. We add up 36 plus 9 plus 4 plus 0 plus 1 plus 9 plus 49. And the sum of the deviation scores is 108. Now, what we do here is we know that n is 7. So to construct the variance, variance is s squared, which is the standard deviation squared. The variance is the sum of the deviation scores squared divided by n minus 1. So this is 108 divided by n minus 1, which is 6. The variance is 18. The standard deviation is simply the square root of the variance. So it's the square root of 18. Which is 4.24. So this is an example of how you would calculate the deviation scores and the variance and resulting standard deviation by hand. Many calculators allow you to enter individual values of x, and then there are functions that allow you to calculate the variance and deviation, or variance and standard deviation, with a couple of pushes of buttons. Now, back when we talked about sections 12.1 and 12.2, that was with regard to descriptive statistics, how to describe the data effectively. In this section, we talk about inferential statistics, that is, how to draw comparisons between populations by analyzing samples that come from those populations. For instance, are they different, and is any difference significant? It's beyond the scope of this course to go into huge detail with regard to statistics, but we're going to touch on them slightly here. So one of the things that we're going to look at is this example. Page 660, number 37. Now let's look at comparing battery lifetimes. Two brands of car batteries, both carrying 6-year warranties, were sampled and tested under controlled conditions. 5 of each brand failed after the number of months shown here. So brand A had months of 74, 65, 70, 64, and 71. And brand B had 69, 70, 62, 72, and 60 months. These are 6-year warranty batteries. Six times 12 is 72. So it should have at least a 72-month cycle of use. So we're going to look at the standard deviations, the mean and the standard deviation of these. And from this, we're going to determine which brand battery apparently lasts longer and which one has the more consistent lifetime. So let's look at the longer value first. So the mean of A calculates out to 68.8 months. And the mean of B calculates out to 66.6 months. The standard deviation of A calculates out to 4.21, and the standard deviation of B calculates out to 5.27. Now remember that standard deviation is a measure of dispersion, that is how far how wide the data are spread. So the first part of the question asks, which brand apparently lasts longer? And it looks to me like brand A lasts longer. The number of months of service are longer, not quite up to the 72 months. But the second part of the question asks, which brand has the most consistent lifetime? And for consistency of life, we need to look at dispersion. So consistency would be equivalent to dispersion. How much spread is there? And once again, it looks like the dispersion for battery A is also less than that of battery B. So not only does battery A last longer, but it's more consistent. There's a tighter distribution here of standard deviation. So we can't only concern ourselves with the mean, but we also have to look at the standard deviation. In addition to this, we need to look at another calculated component called the coefficient of variation. This combines both central tendency and dispersion and expresses the standard deviation as a percentage of the mean. This is described further at the bottom of page 658. Now remember, sometimes the standard deviation is represented by a sigma. Typically what we're talking about is for a sample and a population. So for instance, if you have a population from which you draw a sample, and you perform calculations on this, the mean of the population is referred to by the Greek letter mu, and the standard deviation of the population is referred to as sigma, lowercase sigma. Sometimes this is also called the standard error. In a sample, the mean of the sample is going to be x bar, and the standard deviation is going to be s. So you'll notice that for a population, you have Greek letters, and for the sample, you have Roman letters. These are called population parameters, and these are called sample statistics. So if you just remember that in terms of the first letter of these, population parameters and sample statistics. In section 12.4, we move into measures of position. How do individual data points, that is the X's, fit into the collection or the spread of other data points? And where does it fall? To calculate this, we consider a number called the z-score. And in a normal distribution, we can calculate a z-score based on the sample mean and the sample individual value divided by the standard deviation. So if you turn to page 666, let's talk about this. Look at a couple of examples here. The z-score, the z formula is going to be x minus x bar, that's the individual value of x, minus x bar divided by the standard deviation, which we just talked about. Now, page 666, number 6. Relative performances in track events. In Saturday's track meet, Edgar Espina, a high jumper, jumped 6 feet 3 inches. 6 feet 3 inches. Conference high jump marks for the past season had a mean of 6 feet even. So the mean was 6 feet even. And a standard deviation of 3.5 inches. So this is the individual value of x for Edgar. Kurt Massey, Edgar's teammate, achieved 18 feet. So Kurt achieved 18 feet 4 inches. Obviously, this isn't the same category, but we'll see as we read this through. In the long jump. So Edgar is a high jumper and Kurt is a long jumper. In that event, the conference season average and standard deviation were 16 feet 6 inches and 1 foot 10 inches, respectively. Relative to this past season in this conference, which athlete had a better performance on Saturday? Well, one of the interesting things about z-scores is that it allows us to make comparisons between apples and oranges, as long as we have a mean and a standard deviation. So we're told that Edgar has 6 foot 3 inches, which is 75 inches. Let's convert everything into inches. A mean of 72 inches and a standard deviation of 3.5 inches. So the z-score for Edgar is going to be x minus x bar, or 75, minus 72 divided by 3.5. So that's 3 divided by 3.5. That gives us a z-score of, and we'll round this to the nearest hundredth, 0.86. Now for Kurt, we'll convert his to inches as well. So this is 220 inches. The mean is 198 inches. and 1 foot 10 inches is 22 inches. So the mean for, or the z-score for Kurt is going to be x minus x bar, or 220 minus 198 divided by 22. And that gives us a z-score of 1.0. So the question says, relative to this past season in this conference, which athlete had a better performance on Saturday? And that would have to be the one with a higher z-score, z of 1. Now remember the normal distribution. Oh, that's not very good. Let's look at creating a better normal distribution. Much easier to do this on a board, but let's see what we can do. All right, well, let's say that this is normal distribution. If this is the mean, and one standard deviation is here, and 0.86 standard deviations is here, relative to the mean, this one, the 1, is going to be higher. So this value is going to be higher than this value. So you want to get, the answer to this problem is that Kurt did better in this in his performance relative to the past season in this conference. Let's do another example, number 8. This is page 666, number 8. Remember, z-score is x minus x bar over the standard deviation. Relative ratings of fish caught in a certain lake. The trout average 12 inches in length with a standard deviation of 2.75 inches. This is length. The bass average 4 pounds in weight with a standard deviation of 0.8 pounds. So now we're looking at inches versus pounds. If Toby caught an 18-inch trout, 18-inch trout for Toby, and Katrina caught a 6-pound bass, relatively speaking, which catch was the better trophy? So if we're talking relatively speaking here, we have to calculate the z-scores. So the z-score for Toby's is going to be x minus x bar, so 18 minus 12 divided by 2.75. Which is a z-score of 2.18. And Katrina's z-score is 6 minus 4 divided by 0.8. And this gives a z-score of 2.5. So in this example, this illustration, relatively speaking, Katrina's bass was the better trophy since her z-score was higher than that of Toby's trout. Another standardized score to consider is percentiles. So if we have a certain number, n% of the items in a distribution being less than a certain number, then x, a certain number x, and x is the nth percentile of the distribution. Illustration of this is page 663, example 2. And we'll do some illustrations here in the examples on page 665. $666 actually. So if you turn to page 666 and you look at $666 number 13. Refer to the table at the bottom of page 666. And we're going to look at which country occupied the given position. So in order to figure out which country had the 15th percentile in population, we look at what 15% of the 10 scores are. So 15% of the 10 scores is 0.15 times 10, or 1.5. We look at the 15th percentile, and we have to do this by arranging these populations in order from smallest bottom to the largest at the top. There are 10 scores, so the 15th percentile is going to be the second item up from this. So the second smallest population is going to be Saudi Arabia. For number 14, looking at the third quartile in exports, we have to take 75%, third quartile is 75%, 0.75 times the 10 scores is 7.5, which out of the score of 10 would be roughly the 8th item up. So we look up the exports column. The exports column, if we had ordered these in order, the 8th item up would be China. So related to percentiles are quartiles. Quartiles are the 25th, 50th, and 75th percentile. The second quartile, Q2, is the median value, which is the middle item when the number of items is odd, or the mean of the two middle items when the number is even. We talked about the median earlier in chapter 12. The first quartile, Q1, is the median of all items below Q2. And the third quartile is the median of all items above Q2. These can be illustrated using a box plot, which is a graphical representation of the median, the range, and first and third quartiles. If there are values that are calculated outside the first and third quartiles, they can be illustrated with an outlier point, such as an asterisk. So let's do an example for percentiles. Page 667, number 30. In a national standardized test, Kimberly scored at the 92nd percentile. If 67,500 individuals took the test, about how many scored higher than Kimberly did? Well, if Kimberly was in the 92nd percentile, then 8%, or 100 minus a 92nd, 8%, would have been above her. So 8% times 67,500 is 5,400. So approximately 5,400 students scored higher than Kimberly did. In number 36, relative positions on a standardized chemistry test. Omer and Alessandro participated in the standardization process for a new statewide chemistry test. Within the large group participating, their raw scores and corresponding z-scores were shown here. So Omer and Alessandro had a raw score and a z-score 60 and 72, a z-score of 0.69 and 1.67. Find the overall mean and standard deviation of the distribution of scores and give answers to the two decimal places. Well, remember that the z-score is the individual score, the raw score, minus the mean divided by the standard deviation. So in this case, this is the same test, so the mean and the standard deviation would be the same between the two. So using the data for Omer, we have 0.69 equals 60 minus the mean divided by the standard deviation. So we rearrange this algebraically and we get 0.69s equals 60 minus x bar. And we use Alessandro's data here. We get 1.67 as the z-score equals 72 minus x bar divided by s. We arrange this algebraically. We get 1.67s equals 72 minus x bar. So what we can do here is we can, this forms a system of equations. This is two equations and two unknowns. So what we can do here is we can eliminate one of these by multiplying the top line by -1. If we multiply the top line by -1, we get this. We can add these together. So a negative x bar minus negative x would be 0. So negative 60 plus 72 is 12. And negative 0.69s plus 1.67s gives us 0.98s. We can solve for s by dividing both sides by 0.98. And s equals 12.24. And now that we know what s is, we can plug this back into either of these two equations up here to solve for x bar. So let's do it here. 1.67 times 12.24 equals 72 minus x bar. We solve this by multiplying these together, subtracting 72, and we wind up getting x bar equals 51.55. So the mean is 51.55, and the standard deviation is 12.24. In section 12.5, we explore the normal distribution further. Now, there are a couple of terms here that we need to apply to the normal distribution curve: empirical and theoretical. Empirical means that they're based on observation, but theoretical is based on theoretical probabilities. Remember back when we talked about the probabilities of coin tosses and rolling of dice? Those are theoretical. Empirical are based on observation. But this quote is very, very apropos. The knowledge of theoretical distributions enables us to identify when actual observations are inconsistent with stated assumptions, which is the key to inferential statistics. Now, in Table 1 at the bottom of page 668, you'll see a distribution of coin tosses. Theoretical probability distribution for the discrete random variable number of heads when 5 fair coins are tossed is shown in this table 16. Figure 11, which is also at the bottom of page 668 but not reproduced in this slideshow, shows the corresponding histogram. The probability values can be found using the binomial probability formula from chapter 11 or by Pascal's triangle, which, as you remember, was in chapter 10. What we can do with these types of distributions in a histogram is to smooth them into a normal distribution. A normal distribution is a bell-shaped curve that looks like this. Now let's look at the way that this would work. So if we had a histogram and we drew the bars of a histogram, having a distribution something like this, a smooth distribution curve would just go something like this. So the areas underneath this curve correspond to the areas of the columns in here. In a normal curve, these areas are represented as percentages under the normal curve. The vertical lines on the x-axis of this curve are represented by the number of standard deviations from the mean. So in the very center of the curve, in the high peak of the curve, is the mean. You would expect that that would be the highest value for a normal distribution. This is 0. The z-score for the mean is 0 since there are no standard deviations from itself. So we can go to the left and the right of the mean. To the right of the mean is a positive number of standard deviations from the mean, and to the left of the mean is negative number of standard deviations from the mean. This curve is what they call bell-shaped. Sometimes it's referred to as a Gaussian distribution. It's symmetric about a vertical line that's through its center. The mean, median, and mode of a normal curve are all equal, and they occur at the center of this distribution. Now, there is something called the empirical rule that has to do with the normal curve, and the empirical rule is in the box on page 670. And it tells us that about 68% of all data values of a normal curve lie within 1 standard deviation of the mean in both directions. About 95% within 2 standard deviations, about 99.7% within 3 standard deviations. What this looks like, if I can draw it for you, something like this. Here's the mean. See 1, 2, and 3 standard deviations from the mean. So this region has about 68% of all the data, plus or minus 1 standard deviation, plus or minus 2 standard deviations has about 95% of all the data, and plus or minus 3 standard deviations has about 99.7% of all the data in the entire distribution. This is called the empirical rule. And the normal curve is symmetrical about the mean, so you could theoretically cut it out of a piece of paper and fold it on the mean line, and it would be perfectly symmetrical. So if you look in your book at table 17, this has certain areas under the normal curve. The normal curve areas in the standard normal curve, the following 3 quantities are equivalent. Percentage of total items that lie in an interval, the probability of a random chosen item lying in an interval, and the area under the normal curve along an interval are all equivalent. So you can use the area under the normal curve in order to predict the probability of occurrence of an event. So in example 3 on page 672, the time lengths of phone calls placed through a certain company are distributed normally with a mean of 6 minutes and a standard deviation of 2 minutes. If one call is randomly selected from phone company records, what's the probability that it will have lasted more than 10 minutes? So they give us a normal curve. So the mean is 6, and they tell you that the standard deviation is 2 minutes. So 1 standard deviation from the mean is 8 minutes. 2 standard deviations from the mean is 10 minutes. So if one call is randomly selected from phone company records, the probability that it will have lasted more than 10 minutes has to look like this. More than 10 minutes would be an area of the curve to the right of 10 minutes. So the z-score for this is x minus x bar divided by the standard deviation. So this is 10 minus 6 divided by a standard deviation of 2. So this is a z-score of 2. Now, using the table on page 671, table 17, you have to consider, remember that half of the table, that the normal distribution is 100% of the data, but it's completely split in 2 at the mean. So this entire side is 0.5 of the entire distribution, all the way to the end of the tail on the right here. But the table on page 671 refers to the area between the mean, which is 6 in this case, and our z-score, which is 2. So I'm going to crosshatch this in a different pattern. So we take 0.5, and we subtract this value in the large crosshatched area by going to the column that is marked Z, where you find 2.00, and we find that the corresponding area A is 0.477. We subtract these and we get an area of 0.023. So that means that this area here in the dark shaded area is 0.023 of the area. That's a proportion of the total area. Multiply that by 100 to get percent, and this is 2.3%. So since the standard normal curve has the three quantities being equivalent, percentage, probability, and area, the area under that normal curve is 0.023, 2.3%. So therefore, the probability of the call exceeding that is 2.3%. Remember the z-scores? In order to use table 17, we have to calculate a z-score for the data to be. Example 4 on page 673 includes this illustration. You can look at that at your own, but let's do some exercises from this section of the chapter. Find the percent. This is page 675. Numbers 19 through 22. Find the percent of total area under normal curve between the given values of z. So this is 19. Z equals 1.41 and 1.83. So we have a normal curve. The z-scores are here and here approximately, and they want you to find this area. Remember, the z-score is x minus x bar divided by the standard deviation. That's an x bar there. So the z-score, the area for a z of 1.41 is given as 0.421. An area of 1.83 gives us, or a z of 1.83 gives us an area of 0.466. So this is z of 1.83. This is a z of 1.41. Remember that this table includes this area and this area. So what we have here is the larger area, this one, of 0.466. And then we just subtract the smaller area in here of 0.421. So 0.466 minus 0.421 gives us 0.045 or 4.5%. Problem states find the percent of the total area under the normal curve between these values. And that's how you do it. Remember, 100% of the values are under the normal curve. The normal curve is completely symmetrical, so half of the curve is 0.5. And the table that we have compares the distance from the mean to a given z-score. So number 20 has a z of minus 1.74 and a z of minus 1.14. Now, you'll see that this table, 17, does not have any negative values of z. However, since the table is completely symmetrical, it doesn't matter if the z-scores are positive or negative, you treat them the same way. So the area for a z of negative 1.14 is the same as the area for a z of 1.14. So a z-score of 1.14 gives us a z of an area of 0.373. Similarly, an area of z-score 1.74 is the same as the area of a z of 1.74. And that gives us 0.459. Now, if we're supposed to calculate the area between these two z-scores, once again, the table gives you the area between the mean and that z. So we look at that value, the larger z-score, 0.459, subtract 0.373, 68. So 0.086 or 8.6%. Email me here if there are any questions about this. I don't think we need to do the other two exercises here. Well, maybe we do. Let's do a couple more. We'll do at least one more because on this one we're looking at a z-score that's negative and a z-score that's positive. So we have a normal distribution, the z-score of minus 3.11, and a z-score of 2.06. So we're looking at the total percentage of the percent of the total area under that normal curve between these two z-scores. So once again, the z-score of negative 3.11, the area of a z-score of negative 3.11 is the same as the area of a z-score of 3.11. So we look at the table and we say 3.11 is a z-score of 0.499, 0.499, and an area of 2.06 for a z-score of that gives us 2.06, 0.480. Now, what we've done here is they want the percent of the total area here. So we're not subtracting areas because the table has the value between the mean and each z-score. So the total cross-hatched area is what we're looking for. So we add these two together. So 0.979 or 97.9%. So the problem calls for 100%. Now, sometimes you have to apply the z-score to, or apply what you know about the z-score and the normal curve in order to find the given z value. So let's look at a couple of the illustrations, a couple of the problems on page 675. Look at number 23, where they say 10% of the total area is to the right of z. So in this case, we have a normal curve, and we're looking for a z-score. Remember, area and percent are going to be equivalent. So this area is 10% of the total area, so 0.10. So what we're looking for, since half of the distribution is up here, this half, we're looking for this z-score right here. So in order to find this corresponding z-score, we have this 0.5, and we subtract 0.1 to get this area, the large cross-hatched area, so that we can use this table, table 17, to find a value of the large cross-hatched area of 0.4. This gives us a corresponding z-score of 1.28. So you have to go to the table to find this z-score, excuse me, this area, and you find the corresponding z-score is 1.28. Now this works on the left or right side of the distribution. Number 25 says that 9% of the total area is to the left of a z-score. So in a normal curve, we're looking for this area here, 9%, 0.09. So once again, we realize that half of the distribution is to the left of the mean. So 0.50 minus 0.09 gives us 0.41. We go to table 17. We find an area of table 17. Find an area of 0.41. And we find the corresponding z-score of negative 1.34. Now, the reason the z-score is negative is because the problem states that the area is to the left of that. And any z-score to the left of the mean is going to be negative. Some additional examples for z-scores and applying the normal curve and data and z values are in example 5, 6, and 7. And some other probability examples based on the normal curve are in the exercises that are listed, and also in the syllabus. Let's do an example or two from here. We'll come back to this food for thought in a minute. Page 676. 676, number 44. Filling cartons with milk. A machine that fills quart milk cartons is set up to average 32.2 ounces per carton with a standard deviation. So this is the average with a standard deviation of 1.2 ounces. What is the probability that a filled carton will contain less than 32 ounces of milk? Now we're assuming, it says, assume the following distributions are all normal and use the areas under the normal curve given in table 17 to find the appropriate areas. So we're given that it's a normal curve. The mean is 32.2 ounces. Standard deviation of 1.2 ounces. So the question is, what's the probability that a filled carton will contain less than 32 ounces of milk? So that's our X value, 32 ounces. So remember, the Z-score is the difference, the difference from the mean, the standardized score. So 32 minus 32.2 divided by 1.2. So this gives us 0.2 divided by 1.2. Gives us a Z-score .2 gives us a Z-score of 0.833. No, I'm sorry, I did my calculator wrong. So let's see. Z is 1.66 or 1.67. So that's the Z-score that we're looking at. So we have a normal distribution. X minus X bar. Now, 32, if 32.2 is the mean, and 32 is going to be less than that. 32 is going to be here. So our Z-score is actually going to be a negative value. So they're asking, what's the probability that a filled carton will contain less than that value? So we're looking at a probability distribution, which is equivalent to an area less than this value. So this cross-hatched area is what we're looking for. Remember, table 17 goes by distance from the mean. So it would require us to calculate this large cross-hatched area and subtract it from 0.5. So we go to the table and we look up 1.67. And we see the area is 0.453. Six, 0.453. I'm sorry. I did the wrong math here. 0.2 divided by 1.2. It's not 1.67, it's 0.167. Everybody makes mistakes. So let's correct this mistake. So 0.167. I had the decimal in the wrong place. So we look up the z-score for 0.167. Which is about 0.17. Our table only goes to 2 decimal places, so 0.17 gives us an area of 0.064. So this area here is this area is, we have to look at this z-score, z of 0.5, 0.5 minus the sorry, I was looking at the wrong line. The area is not 0.064, that's for 0.16, but 0.067. Okay, so that's this large area here. The area between the mean and the z is 0.167. So we have to subtract 0.067 from this value, and we get 0.433 for this area. So the area 0.433 is the answer to the problem. Problem states, what is the probability a filled carton will contain less than 32 ounces of milk? And it's 0.433. It's actually 43.3% probability that it would contain less than 32 ounces. All right, let's do another example because that one was confusing. Number 46. The average length of the fish caught in Lake Amatan is 12.3 inches. With a standard deviation of 4.1 inches. Find the probability that a fish caught there will be longer than 18 inches. Again, we're to assume a normal distribution with an average of 12.3. Okay. So our z-score for this x minus x bar over s is 18 minus 12.3 divided by 4.1. 18 minus 12.3 divided by 4.1. is a z-score of 1.39. So they want to know what's the probability of fish caught that will be longer than 18 inches. The z-score is going to be 1.39. And longer than that means in this area of the curve. So we go to the table and we find that a z-score of 1.39 corresponds to an area of 0.418. So this area in here is 0.418. In order to get this area, we have to subtract 0.500 minus 0.418. And that gives us 0.082. So the probability of the fish caught there being longer than 18 inches is 0.082, or about 8.2%. Some food for thought. If the average rate of brain cancer is 0.007%, and given 322.8 million cell phone users in the U.S., as far as June 2011, what is the expected number of cell phone users who are likely to develop cancerous brain tumors? Should we be seriously concerned if we use a cell phone? And if so, should we find a way to stop? Run these numbers and see what the average or what the expected number of people getting brain cancer is. You'd still find a large proportion, over 22,000 people, expecting to develop brain cancer. So we have to consider numbers like this that we get fed by the media that would cause us to make irrational decisions, because the statistics are incomplete. Just take a look at this website. You can find additional information there. Thank you very much for your time and attention.